Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 25. Renormalization as grammar simplification. Tidying up the rulebook when you zoom out. Remember the language we are learning. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are nearing a summit in Book 9.6, Hierarchical Generation, of Episode 9, The Generative Grammar. Our climb through this book has revealed the layered structure of reality. We began with scale-dependent productions, seeing how the same truth can be described at different magnifications. Then we witnessed the birth of emergent grammar rules, entirely new laws and entities, like sound waves and spin waves, appearing when we look at collective behavior. We saw that the coarse-grained picture is not just a blur, it is vibrant with its own dynamics. But this raises a profound and practical question. How exactly do we get from the messy, detailed microscopic rulebook to the clean, effective macroscopic one? Is it just intuitive averaging, or is there a precise, systematic procedure, a grammatical algorithm, that the universe itself uses to simplify its own story as we zoom out? Today, in Part 25, Renormalization as Grammar Simplification. Tidying up the rulebook when you zoom out. We discovered that such a procedure exists. It is one of the most powerful and subtle ideas in modern physics, the renormalization group. It is not merely a technical trick, it is the universe's own method of editing its narrative for clarity at different scales. Our anchor image is a master editor at work on an immense, sprawling manuscript. Picture this editor in a vast library. The manuscript is the complete, fundamental description of a system in the phi language. Every detail, every fluctuation, every microscopic interaction. It is overwhelmingly complex. The editor's job is to produce a shorter, clearer summary for a reader who only cares about the large-scale plot. She does not simply delete random words. She has a systematic method. First, she decides on a new, coarser level of detail. Say, she will combine every 10 lines into one summarized line. She reads the 10 lines, identifies the core action, the recurring themes, the characters that matter for the overall story, and writes one new line that captures their essence. Crucially, she also notes that in doing this, the meaning of some words has changed. A detailed description of a character's nervous tic might, in the summary, simply become part of that character being described as anxious. The word anxious now carries more weight. It is an effective parameter that absorbs the finer details. She then repeats the process on her new summarized version, creating an even shorter summary. With each editing pass, the story becomes simpler, more universal. Minor subplots vanish. Only the most robust, large-scale narrative structures remain. This iterative, systematic editing is renormalization. Today, we learn how the universe performs this editing on the phi field, and how this process explains why so many different microscopic stories lead to the same macroscopic laws. Here's the clarifying puzzle of this part. We have a complex microscopic theory for phi, with many parameters, coupling strengths, masses, charges. When we coarse-grain to get an effective theory at a larger scale, how do we determine the new effective values of these parameters? Do they stay the same? Intuition might say yes, but the mathematics of averaging nonlinear systems says no. Parameters run. They change with scale. How can we predict this change systematically? And what happens if we keep zooming out indefinitely? Do the rules keep changing forever? Or do they converge to a few universal, simplified sets of grammar? The answer is the renormalization group flow. Let's build the idea step by step for our ears. We start with our microscopic phi theory, defined at some shortest length scale, which we can call lambda 0. This theory has a set of coupling constants. Let's give them simple names: G1, G2, G3, and so on. These are like the tuning knobs of the microscopic grammar. They set the strength of various interactions. Now, we want an effective theory at a slightly larger scale, say scale lambda 1, which is twice lambda 0. We coarse grain. We average over Phi's fluctuations that have wavelengths between lambda 0 and lambda 1. This is like the editor combining those 10 lines. After this averaging, we ask, what is the new, effective theory that describes the remaining, longer wavelength Phi fluctuations? We find it has the same form, the same kinds of terms, but with renormalized coupling constants, G1', G2', G3'. Their values are different. Some couplings become larger, some become smaller. A coupling that describes a very short-range interaction might vanish entirely in the coarse-grained picture. It has been edited out. This step, from scale lambda 0 to lambda 1, defines a transformation in the space of possible theories. The key is to iterate. We now take the theory at scale lambda 1, with its new couplings, and we coarse grain again to an even larger scale, lambda 2. This produces another set of renormalized couplings. We can imagine repeating this process over and over, zooming out further each time. This generates a flow in the abstract space of coupling constants. Each point in this space represents a possible set of grammar rules, a theory. The renormalization group flow tells us how the grammar evolves as we change the scale of description. Now, profound things become visible in this flow. First, we find fixed points. These are special sets of coupling constants that do not change under the renormalization flow. They are self-similar. A theory at a fixed point looks the same at all scales. It is scale invariant. These fixed points represent universality classes. Microscopically different systems, if their renormalization flows lead them to the same fixed point, will exhibit identical large-scale critical behavior. This explains why a magnet losing its magnetism, a fluid boiling, and a metal becoming a superconductor can all be described by the same set of critical exponents. They share a universal grammar at the large scale, despite having utterly different microscopic alphabets. Second, we can classify couplings by their behavior near a fixed point. Relevant couplings grow as you zoom out. They dictate the large-scale physics and drive the system away from the fixed point. Irrelevant couplings shrink as you zoom out. They vanish from the large-scale description, which is why microscopic details often don't matter for bulk behavior. Marginal couplings neither grow nor shrink. They require delicate analysis. This classification is the ultimate grammar simplification guide. It tells us which parts of the microscopic rulebook are essential to keep and which can be safely forgotten at any given scale. Let's explore the triunity of renormalization as grammar simplification. The time echo of renormalization, the evolution of effective rates. As we zoom out in space, we also zoom out in time. Fast processes with high frequencies are averaged over. The time echo of renormalization is the running of characteristic timescales. An effective interaction strength, G, that changes with spatial scale, also changes the rates of processes. For example, the effective strength of the electromagnetic interaction, known as the fine structure constant, actually increases slightly as you probe shorter distances, higher energies. This running coupling is a prediction of renormalization. The time echo is this scale-dependent tempo. The speed of interactions is not absolute, it is a function of the narrative's resolution. The space echo of renormalization, the smoothing of texture. With each coarse graining step, the spatial resolution becomes coarser. The space echo is the progressive loss of fine detail and the emergence of smoothed collective variables. The jagged, atomic landscape of a solid smooths into the continuous density field of elasticity theory. The key is that this smoothing is not a loss of information, it is a reorganization. The information about atomic jiggles is packed into new, effective parameters like the shear modulus or Lamé constants. The space echo is this parameterization of texture. The complex microtexture is encoded into a few numbers that define the macro texture. The motion echo of renormalization, the convergence of dynamical laws. The motion of entities, their equations of motion, simplifies along the flow. The motion echo is the flow towards universal dynamical equations. Microscopically, the motion of a fluid element involves complicated many-body collisions. Under renormalization, these details are integrated out, and the motion converges to the Navier-Stokes equations, with effective parameters of viscosity and density. The motion converges to a simpler, more universal choreography that is independent of the precise molecular chaos that gave rise to it. Now let's locate this powerful algorithmic node on the master tree. We are on the Renormalization group branch within book 9.6, Hierarchical Generation. This branch depends on all previous concepts in the book: coarse graining, effective theories, and emergent modes. It enables the final synthesis of the book, reading reality as hierarchical parse trees. It is the computational engine of hierarchical generation, the precise procedure that executes grammar simplification. It is what allows us to move confidently between scales, predicting how laws and parameters transform. To ground this abstract flow, let's light lanterns from clear, familiar contexts. A near lantern from image compression, creating a JPEG or thumbnail. You have a high-resolution photograph, millions of pixels, each with precise color details. This is your microscopic theory. Now you want a smaller file or a thumbnail for a website. You don't just delete pixels randomly. You use an algorithm, like JPEG compression, that coarse grains. It divides the image into blocks, calculates the average color and the dominant patterns within each block, and throws away the fine-scale details that the human eye is less sensitive to. The output is a new, effective image with a smaller file size. The parameters have changed. The exact shade of every pixel is gone, replaced by a blockier representation. If you zoom out, look at the thumbnail from a distance, it still looks like the original photo. This is renormalization. Iterate it, compress the JPEG again and again, and eventually, you'll be left with just a few blobs of color, the fixed point of the image, its most universal, large-scale features. A middle lantern from materials science, the ferromagnetic phase transition. Consider a piece of iron. Microscopically, it's a lattice of atomic spins. The fundamental parameters include the exchange coupling J, the strength of the interaction between neighboring spins, and the temperature T. As you heat the iron towards its Curie point, 771 degrees Celsius, it is about to lose its magnetism. At this critical point, the system becomes scale invariant. Fluctuations of the magnetization occur at all sizes, from atomic to macroscopic. The renormalization group analysis of this system shows that the flow leads to a specific fixed point. The prediction is that near this critical temperature, properties like magnetic susceptibility diverge according to a precise power law. Susceptibility is proportional to the absolute temperature difference from critical raised to the power of negative gamma, where gamma is approximately 1.32. This critical exponent, gamma, is universal. It should be the same for all uniaxial ferromagnets, a universality class, regardless of their specific crystal structure or atomic species. Experiments on iron, nickel, and other materials confirm this stunningly. A far lantern from particle physics, the running of the strong force coupling. In quantum chromodynamics, QCD, the theory of the strong force that binds quarks into protons and neutrons, there is a coupling constant called alpha strong. This coupling controls how strongly quarks interact via gluons. Renormalization predicts that this coupling runs with energy scale. At low energies, large distances, like inside a proton, the coupling is strong. This is confinement. At high energies, short distances, as probed in particle accelerators, the coupling becomes weak. This is asymptotic freedom. This running is not a guess. It is calculated from the renormalization group equations of QCD. Experiments at particle colliders, like the Large Hadron Collider, measure the strength of the strong interaction in high-energy collisions. The data beautifully confirms the predicted logarithmic decrease of alpha strong with increasing energy. The microscopic grammar of QCD, through renormalization, predicts precisely how its own effective strength changes as we zoom in to smaller and smaller scales. From image thumbnails to the loss of magnetism to the liberation of quarks, a universal theme. Systematic coarse graining changes the effective parameters of a theory. This change can be calculated and forms a flow. Where that flow leads, to fixed points or to predictable running, reveals the deep, universal grammar underlying seemingly disparate phenomena. What then is the specific language role of renormalization? It is the grammatical rule of iterative paraphrase and abstraction. It is the production rule that takes a grammar G at scale L and systematically generates a new, simplified grammar G' at scale L'. It is the universe's editorial procedure for generating the hierarchy of effective rulebooks. It answers the meta question: what is the transformation rule for the entire rulebook itself when we change the scale of description? The core question this part asks about phi is: how do the parameters and even the form of the effective equations for the coarse-grained phi field change systematically as we increase the coarse-graining scale? What are the fixed points of this transformation, and what do they tell us about universal behavior? We are moving from static effective theories to the dynamic transformation between them. What does this renormalization procedure do in the generative process? It systematizes the connection between theories at different scales, providing a calculable flow. It explains universality, why diverse microscopic systems share identical critical behavior. It identifies which microscopic details are relevant or irrelevant for large-scale phenomena. It allows us to extract predictions for experimentally measurable scaling laws and running couplings. Now, stability and breakdown. The renormalization group framework is a cornerstone of theoretical physics. It is stable and immensely successful within the domain of systems that are amenable to coarse graining, typically systems with many degrees of freedom and a separation of scales. It breaks down or becomes ill-defined in situations where there is no clear separation of scales or where the fundamental theory is not renormalizable in the technical sense, meaning that infinitely many new parameters would be needed at each step, preventing the flow from being predictive. In the Holophase view, a truly fundamental phi theory must have a renormalization flow that is well-behaved and allows for a finite number of relevant parameters at macroscopic scales. This brings us to the heart of our empirical discipline, falsifiability. The claim that renormalization group flow, derived from a phi-based theory, correctly describes the scale dependence of physical laws is a precise numerical hypothesis. The central claim: for a physical system undergoing a continuous phase transition, like a ferromagnet at the Curie point, the critical exponents, such as beta for magnetization, gamma for susceptibility, nu for correlation length, measured in experiment must belong to the universality class predicted by the renormalization group fixed point analysis of the appropriate phi model for that system. Furthermore, for theories with running couplings, like QCD, the measured dependence of the effective coupling on energy scale must match the renormalization group prediction. Concrete measurement scene, the 3D Ising universality class. We study a simple uniaxial ferromagnet, like the compound lithium holmium fluoride. We can precisely control its temperature near its Curie point, Tc. We perform a series of meticulous measurements. 1. We measure the magnetization, m, as a function of temperature just below Tc. It follows a power law. M is proportional to Tc minus T raised to the power beta. 2. We measure the magnetic susceptibility, chi, as a function of temperature near Tc. It follows chi is proportional to the absolute value of T minus Tc raised to the power negative gamma. 3. We use neutron scattering to measure the correlation length, xi, which diverges as xi is proportional to the absolute value of T minus Tc raised to the power negative nu. The pass condition, validation. The experimentally measured exponents, beta, gamma, nu, are not simple numbers like 1/2. They are peculiar universal decimals. For the 3D Ising universality class, theoretical calculations using renormalization group techniques like the epsilon expansion or high-precision lattice simulations predict. Beta is approximately 0.326, gamma is approximately 1.237, and nu is approximately 0.630. The experimental measurements on our crystal yield values say beta equals 0.327 plus or minus 0.003, gamma equals 1.238 plus or minus 0.004, nu equals 0.629 plus or minus 0.003. The agreement is within error bars. This confirms that the renormalization flow of the effective phi model for a uniaxial magnet, the Ising model, correctly predicts the universal grammar of its critical point. Dozens of different magnetic materials all yield these same numbers, validating the universality claim. The fail condition, falsification. The measured exponents for a well-characterized uniaxial ferromagnet consistently and significantly deviate from the 3D Ising values. For example, if beta is measured as 0.5 repeatedly, or if different materials that are supposedly in the same class give incompatible sets of exponents, The renormalization group classification fails. More dramatically, if we find a system that clearly has a continuous phase transition but shows no power law scaling at all, the changes are abrupt or exponential, it would mean the whole framework of fixed points and scale invariance breaks down for that system. This would be a major challenge, suggesting our understanding of how order emerges at large scales is fundamentally flawed for that class of phenomena. This falsifiability ensures that the powerful abstract machinery of renormalization is forever tied to the precise, sometimes messy, data of real materials. Let's cultivate a practical recognition skill. You can train your mind to recognize renormalization thinking in any situation where a systematic simplification or summarization process changes the effective rules or parameters of the description, and where repeated simplification leads to a small set of universal outcomes. Watch a news cycle unfold. A complex event occurs. The first report is detailed, with many named individuals and specific sequences. As the story is repeated in summaries, on different networks, and in later days, it simplifies. Minor characters drop out. The narrative condenses into a few key themes and labels. The effective parameters of the story, the public's perception of who was at fault, the severity of the event, can even shift as the summarization progresses. Different complex events can converge to the same simplified archetype: a political scandal, a tragic accident. Observe organizational policy creation. A company faces a complex operational issue. Frontline employees have a detailed, nuanced understanding with many local variables. Middle managers create a first summary, turning nuances into a few standard procedures. Senior leadership receives an even higher level summary, leading to a broad policy directive. With each summarization, the effective rules change. The detailed local knowledge is absorbed into the parameters of the higher level policy. Different departments with different local issues might end up governed by the same universal corporate policy after enough layers of summarization. Consider the evolution of a language over centuries. Proto-Indo-European was complex, with many case endings. Through centuries of use, simplification, analogy, erosion of sounds acted like a renormalization flow. Unnecessary grammatical complexities, irrelevant couplings, faded away. The modern Romance languages, though stemming from different dialects, share universal simplified structures, like reliance on word order and prepositions. The flow converged towards a simpler, more analytic grammatical fixed point. Whenever you see a multi-step process of summarization that changes the effective descriptors and converges on a few robust patterns, you are seeing a shadow of renormalization. You are seeing grammar simplification in action. We must connect this ultimate tool deeply to our Holophase journey. In the previous part, we saw new grammar rules emerge. Here, we get the metal procedure for how they emerge and transform. Renormalization is the dynamic algorithmic heart of hierarchical generation. It shows that the universe doesn't just have levels. It has a grammatical dynamics between levels. The five-field story is not just layered. It is continuously edited and refined as we change our perspective. We haven't added a new substance. We've uncovered the metagrammar, the rules for how the rules themselves change with scale. If you want to see the full mathematical derivations and exact equations behind this idea, the formalism of the renormalization group, beta functions for coupling constants, fixed point analysis, epsilon expansion, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. Let us pause and survey the landscape of Book 9.6 from our new height. We have climbed from scale-dependent descriptions to the emergence of new collective laws, and now to the systematic procedure, renormalization, that governs the transformation between these layers. We possess the complete toolkit for understanding hierarchical generation. We see reality not as a static pile of Russian dolls, but as a flowing, self-similar cascade where each level's grammar is a simplified, effective paraphrase of the level below, generated by a precise editorial algorithm. In the final part of this book, we will synthesize all these tools into a single, powerful way of reading the world: hierarchical parse trees. We will learn to see any complex system, a cell, a city, an ecosystem, as a nested grammatical structure, a tree of 5 patterns within 5 patterns, each branch governed by its own effective grammar, all connected by the flow of renormalization. Before we end, the mandatory zoom out to hold our scope. Renormalization, fixed points, running couplings, these are all patterns in the transformation of effective theories, which are themselves patterns in the coarse-grained phi-bar field, which is a pattern in the fundamental phi. We have added no new substances. We have simply discovered the grammar of grammar change. One field, phi, plus its infinite tower of derivative questions, plus the principle of coarse graining, plus the iterative procedure of renormalization. From this, the universe generates not only a hierarchy of laws, but the precise map of how to navigate between them. As we conclude, hold the image of the master editor and her manuscript. The fundamental phi script is the original, impossibly detailed manuscript. Each stable, coarse-grained description, the laws of fluids, of solids, of critical phenomena, is a cleaned-up summary for a particular audience. The renormalization group is her disciplined, iterative editing procedure. And the fixed points, the universality classes, are the timeless, archetypal plot structures that emerge no matter which detailed manuscript she started with. The universe is both the author of the original manuscript and the editor producing all its abridged editions. We have learned to follow the editor's pen, and in doing so, we have learned why so many different stories ultimately rhyme. Salam, and peace be upon you.